John is the President's Professor of Global Climate Change at the University of Alaska Fairbanks. He got his bachelor's from Dartmouth in 1970 and his PhD from the Massachusetts Institute of Technology in 1974. John spent 30 years on the faculty of the University of Illinois. His primary research interests are polar climate, severe weather, and the linkages between the Arctic and the middle latitudes. John was a lead author for the Arctic Climate Impact Assessment and for the Polar Regions chapter of the most recent IPCC assessment. We're very fortunate to have John talking to us today about the scientific need for an Arctic observing network.
Thank you, Mary. When I was given the title for this talk, I started looking around for a good way to structure it. And I found an appealing framework in what's now a famous quote from a former Secretary of Defense of the United States. He said, there are things we know, there are things we know we don't know, and then there are things we don't know we don't know. The third item there cost him his job. But what I found is that this quote relates very nicely to the scientific need for an Arctic observing network. So I'll start with some examples here of some things that we do know. These are things that we know because of observing networks that were put into place elsewhere and in past times. The first one is very basic. It's the increase of CO2 that's been documented. And the reason I put this up here is that we have this record because one person, Charles Keeling, started a CO2 measurement site back in Hawaii in the late 50s, and that has since grown into an observing network for trace gases in the atmosphere. Closely related to that is a figure such as the one Jackie showed this morning, the temperature trends for the past 100 years or so. We have this record because there's an observing system in place to measure temperatures around the world on land surfaces, and we also have ship measurements that fed into this temperature record. Now, there's another observing network that I think showed a lot of foresight, and it's relevant to the issues we've been talking about. That's the baseline surface radiation network. This was put into place in the late 80s. Now, the diagram that's up there shows downwelling infrared radiation. The colored curves are simulations from climate models. And those climate models are driven by, with greenhouse gas forcings as it's been observed up to the present, and then projected amounts into the future. And a couple of the curves have aerosols included as well. Whoops, go back here. There's an important little line here. That black solid line that spans the last 15 years or so is the downward infrared radiation averaged over all these baseline surface radiation measurement sites. And you'll notice that line coincides almost exactly with what the models are simulating in terms of downward infrared radiation, just what greenhouse gases should affect. So as far as the attribution issue goes, I mean, if we're trying to attribute the recent changes to greenhouse gases, a figure like this one could be considered a smoking gun. And we have it because that baseline radiation network was put in place about 15, 20 years ago. A couple of those sites are in the Arctic. One more example of things we know, this is from the Arctic. We know now that not just the extent, but the age of Arctic sea ice is decreasing. This is a figure from the International Arctic Buoy Program, the network of buoys that traces the ice motion. And the group at the University of Washington used that information together with a model to track the age of Arctic sea ice. 1988 is at the upper left. We then step through 2005 down at the lower right. And you can see how the age has decreased from something like 10 years over most of the Arctic down to just a few years over the time frame of a few decades. And we have this information because we've been able to track ice motion using a network of buoys. So with that as an introduction, I'll ease into some of the things that we don't know, starting with this picture of the pattern of temperature changes. We have a pretty good handle on the pattern of the recent warming. This is the warming over the last 50 years, change in the annual mean on the left and the winter temperatures on the right. The main point here is there is regional structure to what's been going on. Carl Erb mentioned this one earlier. The warming is certainly not, or the changes are not uniform across the Arctic. We even have a few areas that show cooling. This area in eastern Siberia and the western North Atlantic have shown a cooling over the last 50 years. So there's more to the story here than just a buildup of greenhouse gases and changes in the downward radiation. The Arctic, in particular, shows a temporal, a rich spectrum of temporal variability. This diagram shows the evolution of temperature anomalies as a function of latitude. The Arctic is up on the top. The reds are the warm episodes, blues are cold. You can see that the Arctic stands out with its variability, not just on the interannual time scale, but on the decadal time scale. So there's been far from a relentless monotonic warming in the high latitudes. And one example that does point to I think our incomplete understanding here is this comparison. That figure on the right is the observed pattern of the winter temperature trends over the last 50 years. That was just up there. The one on the left is a composite of the IPCC model simulated changes of temperature for essentially the same period, the last half of the 20th century. If you compare those two, they're very different patterns. The IPCC models, run with increasing greenhouse gases and their sea ice free to vary, show a warming that's largest over the oceans. In fact, the northern oceans where the sea ice retreats in the model. The observed pattern shows the strongest warming over land. So there are things going on here that we are not able to simulate with fidelity in terms of the observations. So with that as background, I'll focus on 4 things that are in the category of things we know we don't know about the Arctic. And I'll stress how we might apply an observing network to some of these science drivers, as I'd call them. And in every case, I think progress can be made with an integrated Arctic observing network. And I'll start with the local changes. This is another one that Carl Erb referred to earlier. Here's a quote from the Arctic Climate Impact Assessment. It's a statement that summarizes reports from indigenous communities around the Arctic. And the nutshell message here is that the weather for these communities is less stable and less predictable. And if you read the quote there, the bottom line message is the weather is not only less predictable, but it's more variable. Now, this is a fairly important statement. It's the type of thing that has not really been addressed in the scientific literature or in the IPCC reports. The question here is what's going on? How do we explain this loss of predictability and the increased variability that is being seen in Arctic weather? And the ACIA report points out that these reports come from around the Arctic. It's not just one location. Now, the science community is documenting, or just starting to document, an increase in storm activity in the Arctic. Here's an example of one storm north of Alaska. This is the type of storm that seems to be becoming more common. Barrow is right at the arrow in that figure. So that storm's out over the Arctic Ocean. And here is a sort of a time history of the storm counts at Barrow, Alaska. And there has been an increase. So there are some hints here that there are changes in weather systems that might be tied to predictability and to changes in variability. but we're a long way from being able to relate these types of changes to the reports we're getting from communities. So I think here there's potentially very important information in the indigenous community reports. We don't have a good grip on it scientifically, and to get at the root of the changes that are being reported, we're going to need a partnering of indigenous reports and instrumental observations. And in all likelihood, the information we'll need will consist of combinations of variables that have not been measured together yet. And that's pointing right there at the need for an integrated Arctic observing network. The second issue has to do with the fate of sea ice. This is the second example of where there are some fundamental things we don't know. We do know that the sea ice extent over the last several decades has been decreasing. This one's been in the news as well as the scientific literature. The last 5 years have seen these record low summer minima in Arctic sea ice extent. And just by way of an illustration here, that's the ice coverage at the minimum in 1980. There's 2005. You can see by stepping back and forth that we've lost maybe 15 or 20% of the summer ice coverage at the time of the minimum, and that's just in the last 25 years. That loss of sea ice is now starting to show up in the temperature anomalies, the departures from the normal temperatures. We now see in the autumn months that this pattern of warming here is for the autumn season. There's a maximum of the warming right over the zone where the sea ice retreat has been largest in the autumn season. So we are actually starting to see an atmospheric feedback, so to speak, of these changes in sea ice. But the what we don't know part is tied in with the future rate of retreat of sea ice. The ice is going now. How fast is it going to go, assuming it continues to go, through the next century? We do have some projections from the climate models. This one's from the ACIA report showing the retreat during March on the top row and during September on the bottom row. The end of the century is out there on the right, and you see how most of the ice is gone in the summer, according to these models, by the end of the century. But in the winter, there's very little retreat. So we're actually, if these models are right, we may be moving into a new regime where most of the sea ice is first-year ice. And that has some implications for the freshwater budget of the Arctic Ocean. But the interesting figure is this one, which shows the time series of the projected ice loss in the summer from the various IPCC models. So these are the models that are used in the current assessment. You can see a wide range here by the end of the century. Some models have the ice essentially gone by mid-century. Others have quite a bit left by the end of the century. So there's a lot of uncertainty in how rapidly the ice will go. The interesting curve is that black one, which corresponds to the recent history of sea ice. And the message there is the ice seems to be going faster. The retreat is ahead of the pace that the models would have us expect. Whether that continues is an open question. Now, if the models are right, this is what the sea ice coverage will look like at the end of the summer by the end of the century. Basically just a small pocket left near the pole and on the Canadian side of the pole. In terms of attribution, I think we have a lot to learn. I mean, why is the ice going? In all likelihood, there's more involved than just the warming, the increasing air temperatures. This figure summarizes the temperature changes in the intermediate water of the Arctic Ocean between the 1970s and the 1990s. And the orange is water that's essentially above 2 degrees C. You can see how there are signs of warmer water spreading into the intermediate levels of the Arctic Ocean. If you look more closely at the results from some mooring sites, there are moorings actually at the starred locations here, you can actually track these pulses of warmer water through the entryways to the Arctic Ocean. And then even over on the Siberian shelf, you can see these pulses actually reaching the mooring location that's off the Siberian coast. So one of the outstanding questions is the role of this warmer water in the warming of the Arctic Ocean. And in order to get at the answers there, we need to monitor not only the Arctic Ocean more systematically, and that's where the Search and Damocles network that Carl showed comes in, but we also need to knit those measurements together with atmospheric measurements and also with the fluxes of fresh water from the terrestrial part of the system. So there's quite a bit of synthesis of information that's needed here before we come up with a compelling explanation for what's going on with the ice and before we can have some confidence in how rapidly it will go. Third item here, third focus on what we don't know, has to do with the hydrologic cycle. This figure is from Larry Hinsman, pointing out that there are two views on whether the Arctic will become drier or warmer as the decades go on here with increasing greenhouse gases. As evidence that there's some drying going on, here's a picture of some Arctic lakes. These are in Alaska, and you can see how basically the lake is retreating. The shoreline is deeper than it was just several decades ago. And here are some aerial photographs that show the shrinkage of lakes between 1950 and 2000 in Alaska. So there are some pretty widespread indications of shrinking lakes, not just in the Arctic, but over on the Siberian side. There was a paper a year or so ago in Science dealing with the shrinkage of lakes in Siberia. On the other hand, there are indications that the Arctic hydrologic cycle is accelerating. This is a figure from Bruce Peterson showing the discharge from the 6 largest Eurasian rivers over the last 70 years or so. You can see that there is a substantial increase in the discharge over the last several decades. So for whatever reason, at least the runoff from the terrestrial areas is increasing. If you look at the model projections of changes in precipitation for the high latitudes, there is a projected increase of precipitation. The greens and the blues in this diagram are areas of projected increases of precipitation. So both in winter and summer, the increases dominate the picture. There's some drying down in middle latitudes. But according to the models, precipitation should be increasing. So we have some signs, there's some reasons to expect an increase of precipitation, yet we seem to be seeing a drying of at least the terrestrial part of the system in some areas. So there's really a need here to get at the overall drivers and the net effects of the changes in the system. This is a summary of the monitoring needs, which makes the point that there are a number of components that need to be observed and brought together in terms of the interpretation of the recent changes. For a lot of these quantities, especially the evapotranspiration quantities, we don't really have a good quantitative grip on the means right now, let alone the changes that are going on. The picture is complicated here by the permafrost. Vlad Romanovsky will be talking about this afternoon. If permafrost does degrade, continues to degrade, there are going to be changes in the exchanges between the surface layers, the water exchanges between the surface layers and the deeper layers, which will in turn affect the exchanges with the atmosphere. So we've got a complex hydrological system here, certainly over the terrestrial areas of the Arctic. And there, again, is a lot of knitting together of observations that needs to be done before we can assess what's going on and what's likely to happen. The last of the 4 items is this Greenland issue, which has come up several times already today. I think you've already seen the 2 panels on the right, which compare the extent of Greenland melt in 2 years, a decade apart. The panel on the left is, I think, worth looking at because it points out the variability from year to year in the summer melt on Greenland. The The left map is for 1992, which is this point. The one on the right is for the upper point, which was an extreme year. Now, we're having more of these extreme melt years. This is the 2005 picture, which is more like the 2002 one. And there are some areas, the bright red squares there that had not melted in prior years. That was the first time that melt had been detected at those locations. The consequences of the Greenland melt are that there's a potential increase in the freshwater export from the ice sheet. And the ACIA report does make the point that over the last 2 decades, subject to that caveat about the interannual variability, the melt area, at least, has increased by about 16% on the ice sheet. We do have remote sensing information from Greenland. This is a summary of the study using the altimeter data by the group in Norway at the Bergen, the Nansen Center, rather. It's a summary of the changes or the year-to-year variations in thickness of the ice sheet. At higher levels, in red, that's the region above 1,500 meters, and at the lower levels in blue. So those are more the coastal areas. The bottom line here is that there's been a thickening at the upper levels and a thinning at the lower levels. Again, you see a lot of interannual and even decadal scale variability superimposed on the record. So as far as Greenland goes, there are some key questions that call for close watching or close monitoring. One of them is, are we accounting for the natural variability when we point to the increasing discharge? There is certainly interannually and at lower frequencies this variability that I think does need to be reckoned with before we extrapolate too far. The second question is, will the increased melt at low levels outweigh the increased accumulation that we might expect at upper levels? The latest IPCC report points out that the threshold for the answer being yes to that question is a warming somewhere between about 2 degrees and 4.5 degrees. And that's in the range of the actual projected warming from the models that have been run for the IPCC. And then that last question, the potentially important one, what's the fate of the meltwater? In the subpolar North Atlantic, there are already signs that salinity is decreasing. This is a figure from Bob Dixon's group summarizing the salinity changes over 30 years or so in 4 different subpolar seas. All of them show a decrease of salinity, perhaps related to Greenland, perhaps not. The IPCC models project that the ocean meridional overturning, the thermohaline circulation intensity, may or may not drop over the next century. Some models predict a significant slowdown of that deep overturning, others don't. So Greenland is part of this bigger picture where there's a lot of uncertainty. It's the uncertainty in the North Atlantic, in particular the ties to the global ocean through the deep overturning circulation. So the last point will be these possible sources of surprises in the Arctic system. So in that framework we had at the start, these are the things we don't know, or we possibly don't know, we don't know. The ocean thermohaline circulation is clearly on that list. We don't know just what the surprises in that part of the system are. There may well be some surprises in the clouds, the cloud part of the system, since clouds do affect the radiation budget quite strongly in the Arctic. There are probably thresholds and tipping points in the system that we don't know about. And those question marks drive home the point that if we don't know what we don't know, we can't list them on the list of possible surprises here. So I think that fits into the third category of reasons why we do need to monitor the Arctic in an integrated way. And I'll finish with this figure here, which shows life down at the surface in the high latitudes. As this slide implies, the Arctic residents are already coping with changes in the Arctic. We really need to get at the explanations for why these changes are occurring. So there are practical needs for the increased understanding as well as scientific needs. And I think that the monitoring network is going to be the key part of getting at some of the explanations for what's going on. I think this reinforces the need here to partner with the indigenous peoples in an integrated observing network. There's information and experience that we can draw on from them. There's information that we can draw on from the instrumental measurements. And the real challenge is to knit this together, as Carl said, into a sort of a better understanding of what's changing and what's likely to change over the next century or so. So with that, I'll stop and say thank you.
I was wondering about polar low activity. As the ice starts to go away, those are sort of the main hurricanes up there. Is there any weather groups starting to look at increased activity in polar lows? Because for navigation, that starts to wreak havoc up there.
Yeah, in the Alaskan sector, there is a group. It's actually the National Weather Service. And they are documenting a shift in the preferred storm tracks. They're finding more storm tracks north of the Bering in the summer and fewer farther south. Now that's at this point, I think the statistics aren't robust enough to say that there's a convincing shift. But that's the type of thing we would expect to see as the ice edge retreats northward, sort of a shift of the storm tracks. Not all those lows are the classic polar lows. There's been a lot of work done in Scandinavia. Eric Rasmussen has looked at polar lows. I'm not aware of the actual trend estimates, of whether there's an indication that there's a trend over time, but that would be something we'd expect as the ice retreats farther north. There's going to be more open water to feed these storms when they come off the ice. Carl?
John, are there gaps in the subarctic observing network that impact on this problem?
In the North Pacific, I'd say there are, and that's based on experience with the Weather Service. They have difficulty predicting especially the movement of storms into Alaska because of the lack of information that's available for prediction models from the subpolar North Pacific. I'm not as familiar with the North Atlantic situation. We have that salinity tracking from Bob Dixon, which means that there is information out there for some of the ocean variables, but I'm sure they'd like more, and I'm not really in a position to say what the priorities would be for the subpolar seas.
You touched on the hydrologic cycle and changes in the hydrologic cycle. That's notoriously difficult to observe. It's hard to get precipitation numbers, even in populated areas where the precip is rain. In unpopulated areas where it's snow, it's nearly impossible. Evaporation and sublimation are nearly impossible. Could you tell us what's in place right now or planned, and what kind of advances would be necessary before a really robust observation system might be deployed?
I think you put your finger on a real concern, because if anything, the precipitation network has been degrading over time. In countries like Canada and Russia, there are actually fewer sites to measure precipitation on the ground now than there were 20 years ago. One of the hopes is that models that assimilate data may be a way to come up with estimates of precipitation as well as evapotranspiration in an area-wide sense. If the models are really capturing the moisture fluxes and the convergence of moisture, of water vapor in the atmosphere, they may well be a source of precipitation information that's better than what we can get from the present surface network. The group at Colorado, Mark Serez and company, have made some attempts to do that for the Arctic. I think Mark has actually constructed a precipitation climatology based on that approach. Now, whether that will let us get at some of the key variations and the changes over time, I think remains to be seen. But the key will be to have at least enough measurements to assimilate into models that what the models produce Arctic-wide has some credibility. Jim?
Yeah, John, observations from outer space, satellite observations play an important role and have been very helpful in observing such a hard-to-observe system. Could you comment on first, do we have a sufficient array of satellites to do what we should do? And second, are we going in the right direction in the future in terms of having enough observations to prepare us for the changes that are coming?
Well, I mean, I think we're clearly better off than we were 20 years ago. We have the altimeters, for example, to monitor the ice sheets. And there are now satellite data sets of temperature, skin temperature over the Arctic Ocean, which is probably our best source of that type of information. We're still not able to monitor precipitation with any confidence in high latitudes from satellites. We still aren't able to monitor salinity in the upper ocean, although I think the group's working on that one. So I think the answer is sort of a mixed one here. We're making progress, but perhaps certainly not all we'd like. I think the retrieval of atmospheric profiles, temperature and humidity, has come a long way. The trick there will be to assimilate that again into models in a way that improves the overall system state that comes out of these models. So it's a multifaceted question there, and I think there are some successes to point to and still some pretty hefty gaps.
One more question?
There's one over there.
I just had sort of or two comments. One was just in response to Jim. Certainly, where we live at UNH with Barry Moore being on the decadal survey for observations from space, he's making a lot of noise saying that we're poised to go downhill from where we are now. Things don't change, certainly with NASA's funding. But a lot of these resources we have, satellites, are going to run out of their lifetime, and the plans to replenish them are not very firm within the U.S., so hopefully there's other nations getting more and more interested. The other question or comment was, on that Greenland question, I'm very curious. Well, I think that one of the other big unknowns is what's this trend in the drawdown of the ice sheet through the outlet glacier. You didn't even mention, but there's a lot of recent press saying that it's speeding up. Is that going to continue or not?
Yeah, and that's one that the IPCC ducked. They were willing to assume that the discharge, the meltwater runoff would increase at the present rate of increase, but they essentially threw up their hands when it came to the changes in the dynamics, basically the changes in the dynamical discharge. So I think that is that's a glaring need as far as the water budget goes. And for whatever reason, the IPCC did not feel that there was enough information in hand to say anything confidently about it.
Well, I was just saying, it should be on one of your we don't know, or whatever on your list, if you take this talk somewhere else.
Yeah, okay.
Big question.
Good, thanks.
I want to have everybody thank John, and then I'm going to tell you about one. In 2008, the Arctic Science Summit Week will be held in Russia, and their speaker will not be here until tomorrow. So during Project Day, there will be a brief presentations by the Russians welcoming you to Arctic Science Summit Week 2008. But this is just a heads up of that. Okay. We have a very interesting afternoon program. I'm glad to see so many people back from lunch. Our speaker this afternoon is Dr. Len Berry. Len is the director of the Atmospheric Research and Environment Program at the World Meteorological Organization. Len has had many career highlights. I'll just mention a few. And he originally joined the Meteorological Service of Canada, of Environment Canada. So he has worked in Canada. He's worked closely with U.S. and people from many nations on that, looking at lead isotope and interactions in the Arctic boundary layer with ozone depletion, were some of the highlights of his own research along with acid rain research. Then in 1999, he joined the Pacific Northwest National Laboratory as the chief scientist there. In June of 2002, he was picked off by the World Meteorological Organization of Geneva, invited to be the chief of the Environment Division in charge of coordinating the Global Atmospheric Watch Program, the GAW program. And in September 2006, just this last September, he became the director of the Atmospheric Research and Environment Program of WMO, in charge of the Global Atmospheric Watch, GAW, the World Weather Research Program, and Thorpex. And so these are all, it's great to have Len here because he has extensive experience as a scientist. He's worked with many organizations, and he has really a global view of what's going on. We're happy to have Len Barry here to speak about the atmosphere.
Am I okay, Barry? Oh, we need to turn it on. That's a on the end here.
Yeah.
Okay. Thanks, Mary. It's indeed a pleasure to be here at this forum and have the opportunity to hear from so many different perspectives the importance of polar region. Polar regions have been very close to my heart all of my career as a hybrid meteorologist, atmospheric chemist. And what I'd like to do in the 20 minutes or so, or 25 minutes or so that I have, is to hit some highlights on what has happened in the polar regions, specifically, particularly the Arctic, with regard to Arctic air chemistry, which really is a relatively new field compared to some of the more classic polar research areas, such as the geophysical area or meteorological, for that matter. So let me start.
Sorry.
But basically, by saying that I'm wearing two hats here. One is an Arctic air atmospheric scientist. The other one is, as Mary mentioned, director of the Atmospheric Research Environment Program from WMO. And I'd like to highlight or emphasize that the IPY is co-sponsored by, at the top, as we heard this morning, by the World Meteorological Organization and the International Council of Unions for a very good reason. And that is, much like one sees at the national levels, the mix between process-oriented research and long-term, more facility-based government research, there is also a need for this internationally, and the WMO-ICSU combination is a very good one for that. This report has just come out on the website for anybody who wants to see it. Now, I like this picture of the polar regions for a couple of reasons. One, it drives home the tremendous contrast between the South Pole and the North Pole. That continent of ice peaking at 4 kilometers around South Pole, surrounded by the roaring 40s to 60s in the Pacific Ocean, remote from industrial pollution that is medium aged, therefore is relatively clean compared to the Arctic, which in turn is surrounded by industrialized continents, has a very flat surface underlying it The topography in the north being mainly the mountains of North America, Greenland's 3-kilometer thick ice cap, and the mountains of Asia. And underlying the polar atmosphere is this very thin membrane of ice separating it from the Arctic Ocean, which is in turn a very unique ocean, which has been at once called a Mediterranean of the North, because it has basically one inflow, and one outflow, with a little bit of leakage in from Bering Strait. Very, very interesting contrasts. But global pollution that is long-lived affects both. The greenhouse gases, for instance, the perfluorocarbons. Just before I carry on, I'd like to acknowledge some colleagues who've contributed to this talk and who've joined me over the years, many of them. We have some new faces like Anna Jones and Andreas Stoll, and they're in the audience here, colleagues that have worked with me on Arctic air chemistry for many years. What is our motivation for studying polar air chemistry? And these 6 points, I think, summarize it in my mind. Of course, climate. Weather underpins climate and is basically driven by the same forcings. Aerosols, ozone, and greenhouse gases are essential climate variables, and the numerical weather prediction community are now beginning to realize that at least aerosols and ozone are essential weather variables and need to be assimilated along with classic meteorological variables to enhance weather prediction. We have the toxics and the cycles of nutrients and the toxics, POPs and mercury, which have played a big role in our Arctic and polar research. For the POPs issue, it has been really the world as a large gas chromatograph. And that issue has been dealt with to some extent, and the program is rather mature, and things are well understood. Mercury is an interesting issue that I'll come back to, something that we did not know about that has some very fundamental processes that take place in the Arctic, and they'll appear as I talk about some of the discoveries that have taken place over the years. Another important reason for studying polar region chemistry is to better understand the transfer function between atmosphere and glacial ice cores. And when I started out my career in the 1970s, and many of us here, there was a very simplistic model of chemical transfer between atmosphere and glaciers, with very little transformation, post-depositional transformation. And that whole thing has been turned on its head in the last 15 to 20 years. And I'll show you a few examples of that. And another reason for studying the polar regions and atmospheric chemistry is that they're just wonderful planetary system laboratories with the contrasts between the Antarctic and the Arctic, the natural experiment of pollution being inserted into the polar regions of the Arctic and less so in the Antarctic. We can ask questions by comparing them, and we've learned a lot. The climate issue is definitely driven by atmospheric chemistry. This diagram alone shows greenhouse gases, black carbon on snow, which is a new thing from 2002, aerosols and their effect directly through direct coupling to solar radiation and infrared radiation in clear skies, but also through their interactions with clouds. So there is good reason for us to be concerned with chemicals in the polar regions from the point of view of climate and weather. which sometimes I think just gets, it goes without saying, no one mentions it. And I'll come back to something John Walsh mentioned this morning about something we know we don't know. This is just a reminder, John covered it this morning, that in a future climate scenario, this is one of those global climate models from the Hadley Center, and basically one of the emission scenario, one of the emission scenario from the IPCC that sort of, this is business as usual, and this is sort of a best estimate of what might happen scenario. We are definitely going to see big changes in the polar regions. Greenhouse gases have reached levels higher than they've ever been in the last 800,000 years. This is just a reconstruction of the atmospheric composition from the last 60,000. The green and red are constructed from instrumental records, the rest largely from glaciers. This instrumental record is put together in a very systematic way through a global club, I might call it, that is called the Global Atmosphere Watch Program. This happens to be the carbon greenhouse gas segment of our program. It also involves ozone UV, aerosols, and reactive gases. And this is what we have right now for a systematic observational network for greenhouse gases globally. Largely, about 70% of these sites, excuse me, I'll go back here. 70% of these sites are NOAA GMD laboratory. NOAA GMD laboratory took over the stewardship of the Mauna Loa, Hawaii record and expanded the network from one to many stations in 1975. And at that point, WMO began sponsoring carbon dioxide and greenhouse gas measurement group every 2 years. And the last group is met in Boulder for its 30th anniversary just a year and a half ago, and we'll meet in Helsinki this September. We have a very mature program that is based on research operational community. And I draw the distinction here between operational in the classic meteorological sense and a research operational in a atmospheric chemistry sense, because there is a different mode of operation required by atmospheric chemistry generally than for some of the simpler classical meteorological variables in doing systematic observations. And that is a subtlety, I think, that is often missed in managing programs. Kinds of products that this community produces is shown here. The greenhouse gas bulletin showing that CO2 is indeed going up and is increasing, has an average growth rate of roughly 1.8 ppm per year. We have laboratories on the ground, surface in situ, continuous, like South Pole, like Alert, Barrow, beside it in the Arctic. We have ship measurements, flasks sampling being taken on ships. We have systematic routine aircraft measurements being done by Japan Airlines. This will be soon joined by the European Airbus. And we do not yet have a CO2 satellite measurement of carbon dioxide. Skiamaki is starting to recover some carbon dioxide, but it's doing very well with methane. There are AIRS and IASI for upper tropospheric CO2, and an orbiting carbon observatory, and the GOSAT by satellites that are coming online. So this sort of integrated observation system is available for greenhouse CO2 and methane. Another radiative forcer, and this is a nice nice piece of work that has just been published in the last year and a half or so by the NASA GIS people, basically pointing out that in the winter Arctic troposphere, anthropogenic ozone, which is formed from photochemistry further south and advected around the Arctic region in the colder part of the year, December to May, the lifetime of ozone in the troposphere is much longer than it is down here at mid-latitudes. It can be up to 100 days long. That this ozone comprises approximately 1/3 to 1/2 of the total greenhouse gas forcing in the Arctic air mass in the winter, and has quite a heterogeneous pattern because of it is a less long-lived gas, so has distribution, and needs to be taken into account in the energy budget of the Arctic troposphere. That's one of the things we don't do right now that John was mentioning this morning. This is a picture from Spitsbergen on a clean day, and this is a picture from Spitsbergen on a dirty day. Advection of aerosols into the Arctic we've known about from Arctic haze since we began studying it in the late 70s and realized that by the mid-80s that it was widespread, 20 to 40 times higher in the lower troposphere in the winter half of the year than in the summer half, and coming and advecting into the Arctic from the continents around. This is a picture that Ken Ron, one of the original discoverers of Arctic haze at Barrow, put together with a little nudge from myself as well, showing the pathways in the lower troposphere driven in the winter half of the year. These pathways look very different as you go up in the atmosphere, and things become the flow becomes more concentric around the pole and a lot faster. The Arctic is surrounded by anthropogenic emissions, here indicated by the SO2 gridded emissions that were published by the AMAP assessment. This SO2 is converted into sulfate aerosols, and it's also a surrogate for nitrogen oxides and other pollution. I might point out that one grid here at Norilsk has perhaps the highest emissions of all in anywhere, and we miss it in these kind of things. But there are a lot of big sources, point sources that are embedded in this distribution. Now, leaping to the other pole, the Antarctic ozone depletion situation is driven by anthropogenic long-lived bromine, fluorine compounds whose destruction of ozone require a catalyst, and that is ice clouds, which are intimately linked to climate. As greenhouse gases increase in the atmosphere, the stratosphere tends to cool. We tend to get more polar stratospheric clouds. And the whole issue of will we return after perfluorocarbons decay away to a pre-1980 level of stratospheric ozone is a moot point, because we will not return in climate-wise to the original atmosphere. And the reactions are all driven by temperature, and so it's unlikely that the same state will be returned to. There are two bulletins issued by the WMO. Gare Bratton is currently the ozone officer working in our department. He's begun to issue, in addition to this Antarctic ozone bulletin, which tracks the situation each year, an Arctic ozone bulletin, which shows that indeed the Arctic, basically nothing has begun to improve in the polar regions yet. Even though the production of the most reactive perfluorocarbons for ozone depletion has been stopped, because their lifetime is so long, it will take 50 to 100 years before they decay away. And so we're stuck with ozone depletion for quite a long time. And if anything should happen to add ozone-depleting substances in the meantime, then it'll come back to us. Leaping from the upper troposphere down to the upper atmosphere, stratosphere, down to the surface, perhaps some of you know about the tropospheric polar sunrise ozone depletion situation. This just summarizes a long time series of measurements that have been made at Alert, Barrow, and Spitsbergen, showing that in the springtime there is a very high variability of ozone and very many ozone depletion events. And this was something that Sam Altmans and Walt Kummer from NOAA CMDL lab, or NOAA now, published back in 1983. They didn't quite understand why the springtime ozone was fluctuating like crazy. We went and did a very simple experiment. I'd been measuring bromine at Alert for many years and saw every springtime an aerosol bromine peak. Ken Ron had also seen it at Barrow, and we were also speculating. This sort of higher resolution observations showed that bromine and ozone depletion are linked at the ground. And the question was, where does it come from? And all of this led to, and the reason I'm showing this, some of it's old hat to some of you, is that all of this was totally unanticipated, some would say perhaps trivial information as far as impacts on climate or other. But it was a very fundamental value and has many implications. This is just the kind of chemistry that we think is going on producing the bromine that helps deplete the ozone and leads to particulate bromine formation. But it not only does that, it also, this photochemistry on the surface involving sea salt, also in non-sea salt areas such as Summit can also, this photochemistry can also mobilize nitrates to NO. And particularly over the Arctic Ocean, it can also, the BRO can play a role by converting elemental mercury, which is mainly in the gas phase, and is the main bearer of mercury in the atmosphere. It's the only metal that has mainly gas phase component. Converting it to a particulate, which has a very short lifetime and therefore is deposited much faster. This is one of the first composite climatologies of BRO that was put together for a paper in GRL by Bill Schroeder and ourselves, by Andreas Richter from the Skiamaki satellite, showing BRO in the springtime. And for this, we realize now, for BRO to be in the atmosphere, you need ozone above snowpack with sea salt and sunlight. And you need a snowpack that is not wet. It has to be a frozen snowpack. That seems to be the main criteria. And there's scads of BRO in the Arctic in the springtime. And it results in enhanced mercury deposition in the polar regions. Compared to, for instance, I'll just use, this was in the springtime snowpack, a survey that was done just after the Sheba experiment. This is just a snowpack sample from Lake Winnipeg here, this little bar, very remote from where we see the BRO, and elevated levels throughout the region that I just showed you. Seem to be missing. And frost flowers on the Arctic Ocean surface after refrozen leads are one prime candidate for the source of sea salt that we find in the snowpack throughout the Arctic Ocean. Horizontal blowing, drifting can cause, I think, migration of a lot of sea salt. At stations like Summit, there is a great deal of work that is going on at this elevated 3-kilometer high observatory. It's our only, in the Global Atmosphere Watch Program, high altitude observatory in the northern polar region. The South Pole at 4 kilometers are our only high altitude middle troposphere or upper middle in the southern polar region. Jack Dibb has done a lot of work with colleagues in this summit, looking at snowpack exchange and the transfer function to glaciers. And Jack's summary here underlines what I was saying before, that this was our preconceived idea 25 years ago about transfer. And today, it is a very different picture we have in our mind. And this kind of picture is going on between atmosphere and snow out here in sunlight, as well as in the Arctic, and can impact on urban photochemistry in the springtime in certain regions. So let me move on to some of the IPY activities that are going on. I mentioned Andreas Stoll and a group of scientists who are going to be focusing on chemistry, aerosols, and transport in the Arctic, and polar cat. They will be using aircraft platforms as well as observatories. There will be OASIS. There's posters out here, by the way, for polar cat. OASIS, Paul Shepson and Jan Bottenheim are here from that group. Patty Matrai from the ocean biogeochemistry community, looking at basically the processes at the interface. Things like how natural gas exchange of sulfur compounds are affected, how BRO impacts on mercury, what is the net deposition, what is the nutrient transfer of, what is the impact on nitrates, etc. We were talking about an Arctic observing network this morning, and this is very much in the flavor of a strategy that was published in September '94 for the Integrated Global Observing Strategy, IGOS, that I co-convened a group with Jörg Langen of ESA and a panel of atmospheric scientists around the world to come up with a strategy for integrated global atmospheric chemistry observations. In short, what that meant was we needed to have a systematic approach to bringing all types of observations of a particular variable together in a smart way with models, and linking the products of that interpolation synthesis to users and users' needs. That's the bottom line, I think. And to do that, quality assurance activities are absolutely fundamental, and that hasn't been mentioned yet, and I think it needs to be. That mergeability, we need to have data of known quality in order to integrate. And this is a hard job. It's not something that you enter into lightly. And so an Arctic observing, at least from the air chemistry point of view, an Arctic observing network needs to have adequate resourcing and paid to this aspect. What do we have right now for systems? Satellites for air chemistry in the polar region are good in the light, but the polar regions are in the dark for half of the time. And certainly those substances that need solar radiation to be measured, and there's quite a few of them. So satellites have problems, and there needs to be work on specialized satellites for the polar regions. The Calypso LiDAR instrument that is being flown by NASA now on the A-train, I think is going to give us some very nice synthesis of aerosol. Models have their problems in the polar regions because of the stability of the atmosphere, because of the pole problem. What do we have for established Arctic air chemistry observatories that have been running for quite a while? and are likely to run for quite a while. I think this is my first cut at it. Maybe I'm missing, I apologize if I'm missing anybody's favorite spot, but these are basically global atmosphere watch stations coupled with NDAC stations for stratosphere. Chemical buoys in the OASIS program being developed for the polar region, I think, are going to add to our arsenal of systematic observations. There's a poster out there on this. I don't think we've used the nuclear icebreaker capabilities of the Russian icebreakers adequately from a point of view of atmospheric chemistry. They're the cleanest platform you can get. They're nuclear. Compared to the Louis Saint Laurent and the Polar Sea here on the expedition back in the late 90s. It's a nightmare for an atmospheric chemist to work on those things. I know because I was responsible for a package on the Polar Sea. So I think there should, if we're talking about a systematic observation, let's get these nuclear icebreakers involved. I was just reading on the way here in the flight magazine that it costs a tourist $25,000 to go to the pole on these. They're used commercially. And this is at the North Pole, by the way. And I'll stop here. I think that the idea of a systematic Arctic observational network is a great one. And it really needs to have a mix of the university research community and the solid facilities underpinning that the government research facilities can bring to it as well.
We have time for several questions, and I'm going to ask Len to repeat the question so that people can hear it back. Question?
Len, so there are a couple of interesting, maybe competing changes going on about ozone for the future. All around the Arctic Ocean, there will be increasing emissions of the precursors contributing to the ozone part of the warming in the Arctic. But at the same time, as John talked about earlier, there will be increases in first-year sea ice, and the first year of sea ice might contribute to more extensive ozone depletion in the surface layer. So I'm wondering what your thoughts are about the future of tropospheric ozone in the Arctic and the picture of long-term monitoring of ozone in the Arctic. Do we have what we need to watch this unfold for the rest of the century?
Do I have to repeat that question? Did everybody mostly hear that? That's a tough one, Paul. Of course, I think charity begins at home when we're talking about what we have already. Do we have the appropriate measurements at the existing observatories would be my first question. Can we put something on the buoys? Or we don't have very many within the ice overwintering measurements. The Sheba ship is missing ozone throughout the whole winter, which is a tragedy, I think. I think we need to do some simple things with simple, robust instrumentation that we have as our first step. And a lot will be learned from it.
Other questions?
Thanks, Mary.
Our next speaker is Harold Lang from Norway and the Institute of Marine Research. And I actually don't have his bio here, but he has been a key figure in several major efforts. I believe that on the IPCC, he was a lead author on the marine ecosystems. And I'm going to ask Harold to tell us more about it. Welcome, Harold.
Thank you, and thank you for inviting me. It's a pleasure to be here. I've not been involved in IPCC, but I was involved in Arctic Climate Impact Assessment that was initiated by AMAP once in time, and was responsible for the marine chapter in that volume. What I'm going to talk about today is marine ecosystems in a changing climate. And I have to apologize, I'm going to show a couple of figures that are quite similar to what John Walsh showed you earlier today, but that's because I think it's important to have some background about the physical conditions before we talk about the impact on the ecosystems. And I'm just going to show a couple of examples from the ecosystem. I'm going to show some examples from climate impact on phytoplankton, especially the Arctic Ocean, based on the model from Eddie Carmack, and then some examples on how is impact on fish stocks. As we can see in the right-hand corner, there is a lot of concern about climate for the moment, and this is the front page of a German report that was just prepared last year for the German government, and showing that there's a lot of concern now about what climate is changing and what impact it will have on both humans and marine ecosystems, and also other terrestrial ecosystems. This is from an average, or kind of an average of a medium expectation of climate change in the future. And we see that with one small exception over the Labrador Sea, there will be a warming all over, and pretty good warming, 4 to 5 degrees in average, while we over the Labrador Sea will have no increase or maybe a slight small cooling, which might be very important for the thermal circulation, because there is one of the places where deep water or dense deep water is formated, and this is a good sign for those who think that's a main driving force for the thermal circulation. As we have seen earlier, there has been a reduction in sea ice during the last year, and about 20% reduction in sea ice during the last 25 years. And if we are going to test the models, we see that it will be continue to decrease in the future. And the different colors here, the blue and red and green, are different scenarios, and the panels are different models. And we see that for a couple of models, the Arctic will be free of ice during summer already about 2070. And that's will have dramatic impact for some marine mammals, especially the polar bears. I will return to that. The meridional overturning is a broader expression than the thermal circulation. It includes all the currents that's going from north to south. And so far, there is no evidence for change or trends in the meridional overturning circulation. So there have been a lot of observations, but there is no indication that it changed lately. And we see that in this area, we have the formation of deep water or the dense deep water that go to the bottom and make the driving force for the conveyor belt. And as we saw, the cooling will still go on in this area in the future also, while this area north in the Greenland Sea will have a warming, and we should expect a less formation of dense water in this area. It's expected that, or most of the models at least, indicate a reduction in this meridional overturning circulation in the future, about 25 to 30%. But the temperature in the Atlantic region will still increase because of much larger warming associated with the increased greenhouse gases. And it's also very unlikely that the MOC will undergo a large, abrupt transition during the 21st century. This is from the last IPCC report. So I guess this is what we should expect also in the future. And then, you should also remember there are different scales for changes, both in time and in area. And we see that the short-term variations have impact on smaller area, while these long-term changes have impact on much larger areas. And if you go to the corner, the Origo down here, we are down to the turbulence area, which is going on in seconds. There are at least, maybe several types, but just to illustrate the difference between the short-term or interannual variability and up to decadal, we see in the upper, the red one, it's a much larger amplitude. It can be up to 2, 3, 4 degrees in some areas, while the multidecadal changes are much smaller, and it's only, let's say, plus minus 1 degree from the average. And this interannual to decadal are added to the multidecadal ones. So if the multidecadal one is increasing, we will have a more strong increase during these maximum values, while if we have a decreasing trend there in the multidecadal one, that will reduce also the future warming. So this is something we should remember. We don't need to have the same warming throughout the whole time. So if we are going into a phase in the future, the next 20 years with a decreased multidecadal trend, that will reduce the expected anthropogenic increase in temperature. The marine ecosystem is a bit complicated, and this is just a drawing that is prepared at my institute, and at least indicates some of the organisms living in the sea. And these organisms are also very closely linked to each other, and it makes it very complicated when you are going to look at impact from climate variability on these different organisms. We can have a closer look at some of this. We start on the bottom with phytoplankton, which is a basic of everything. And then we have some of the zooplankton, mainly colonus species. This is Colonus fimachus. And then we have the pelagic fishes that feed on zooplankton, and then we have the big demersal fishes that feed on the smaller pelagic ones. But the ecosystem has changed throughout the times, and the oldest observation I know about that is published is from 1576. It's from a map showing organisms living in outside Norway at that time, and if you have a closer look, we can see that the organism that lived that time was quite different from what we have now. and I think we should trust these figures because they have a very nice figures here from reindeer herding in northern Norway, and the drawings of the reindeer are very clear. So I guess we should also rely on the figures in the sea, and this is in a way explain why these species now are not seen anymore, because it was a heavy catching effort at that time of these species. And since they're big, they reproduce very slowly, and maybe and also some climate change that had influence. So this has gone, unfortunately. So we can see that there have been changes throughout times. Plankton, the climate impact on ecosystems, on plankton, as I'm going to start about, and then I'm going to show some example on how is an impact on individual growth of fish species, recruitment, distribution, and migrations. And I will also say a few words about marine mammals. This is a figure from the Arctic Climate Impact Assessment that was prepared by George Hunt in 2002, showing the phytoplankton production in the Bering Sea. And when we had an early ice retreat, there is a very good production of zooplankton in this area. I don't know the linkage here, but and I don't know if they can explain it either, but it seems that an early ice retreat is very good for the zooplankton production, while a late ice retreat is not that good. We then get a less or lower production of zooplankton. And what we should expect in the future with an increased temperature is the upper panel. What we also expect in the future, this is also from the Arctic Climate Impact Assessment, and there are two figures here. The upper one, or upper panel, is the light conditions. If the ice disappears earlier in the spring, we will get more light brought to the ocean, and we get increased light to the sea early in the spring, which will start increase the phytoplankton production earlier stage. And in the autumn, when we have a later freezing, you will have wind impact on the ocean that will mix the ocean and transport nutrients from the deeper layer up to the surface layer. And altogether, these two will give better conditions for phytoplankton production in the Arctic Ocean or in ice-covered areas in the Arctic. If we look at, this is from Eddie Carmack, the blue dotted line here is the summer ice extent today, and we see that's mainly on the shelf break, while in the future we will have the ice border will more or less follow the red dotted line here, and that means that we will have the ice concentrated to the deep Arctic Ocean. And that will have impact on the production, because as it is today, there is no, when the wind is blowing, there will be no upwelling or at the end here. But if we have moved the ice edge, as we see at the lower panel, there will be a lot of water transported from the shelf and then need to be compensated, and we will get an upwelling along the shelf from the deep nutrient-rich water into the shelf, which will increase the production in the area. And the model show that there will be the increased flux of nitrate to that area. And we especially see that seas like the Chukchi Sea and the Beaufort Sea will have a large increase of nutrients if this is the case in the future. That was, it's sometimes slow in its reaction here. And this will also show the increase in new productions in the area. And we see that some areas like the Barents Sea that have very little ice today will have a very little new production, while areas like the Beaufort Sea and the northern Canadian archipelago will have much more new production in the future, if we should believe this model from Eddie Carmack. But it's a very logical thinking, and I think this is illustrate what we could expect in the future. On fish stocks, as I said, this is very complicated, and I'm not going to try to explain this in detail. But there's a lot of parameters that are involved here, and we should remember that climate is more than temperature. we only talk about temperature mainly, but it's much more. We have changes in salinity, we have changes in light conditions, as we have mentioned already. We have changes in turbulent conditions, advection and vertical mixing, sea ice and all this. And all this have some impact on the different levels in the food web. In addition, we have an indirect effect that goes through the food web from phytoplankton, zooplankton, planktivorous fish, larger fish, and up to marine mammals. So there's both a direct and indirect effect of climate on the ecosystem. And back to the figure showed here that there are this interdecadal or interannual to decadal variation have a local impact on local production on lower trophic levels, and they have impact on fish recruitment and year class strength, while the more multi-decadal one has impact on habitat extents of population, for example, the spreading of benthic fauna, and also production on higher trophic levels. So we can see that there's a different impact on short-term climatic variations and longer-term variations. This is just to show the temperature impact on fish growth. And this is fish that are 4 years old from different areas. And we see that cod that grow up in the Labrador and the Grand Banks are the smallest one because they live in the coldest waters, while the cod from the Irish Sea that live or grow up in 10 degrees centigrade are the fastest growing cod. So if the temperature will increase, we should expect a better increase in this species, growth in this species in the future. This is showing, however, the recruitment. And in waters, this is not very convincing necessarily, but on the left-hand side, we have examples from the cold areas. And if we get an increased temperature, we will expect an increased or improved recruitment in these areas. While in the areas that are pretty warm already, like the North Sea, Irish Sea, and the Celtic Sea, where its temperature already is high, we may expect a decrease in recruitment. So that means that in cold areas, we should expect a better recruitment in the future, while in the warm areas, we should expect a lower recruitment. And this is again an example from the Bering Sea, from George Hunt, showing that during cold regime, there are very low recruitment and very little fish, while when we get the beginning of a warm period, we get more zooplankton production, we get a better recruitment of fishes, and the fish stock grows dramatically. And in the third panel here, but then they have reached a big size, the fish stock, so they start feeding on their own larvae, so the recruitment are going down. And if you're then getting a colder climate again, we still have a huge fish stock, bad recruitment, and there will be very little recruits or juveniles at the end, because there are some cannibalisms within the stocks. This is one of the best examples showing how climate has impact on distribution of species. This is from Greenland in the 90s, from 1900 up to end of the late 30s. And we see in the beginning of the century, or already or also in 1917, 1918, we had cod very far south in Greenland, while in 1937, 38, it's up to 75 degrees. And that's a distance of 1,500 kilometers, which is pretty a long distance. And we might expect changes like this also in the distribution in the future if the temperature are increasing again. This is an example from the Northeast Atlantic, where we have different species. And what we are seeing now is that some of the blue whiting that have been living in the Norwegian Sea have migrated further north and east and into the Barents Sea, and we have observed more than 1 million tons of blue whiting in the Barents Sea in the last years. Mackerel, that usually is a fish that lived in the North Sea or southern Norwegian Sea, have also been observed north to 70 degrees. And capelin and cod has moved farther north and east in the Barents Sea when the temperature increases. What we might expect in the future, if this temperature is increasing, is that some of the species living in this area moves up to the Barents Sea. And we don't know what's happening when new species are introduced into an ecosystems that have been established for many years. And this is valid for all kinds of ecosystems in the north, because if species are migrating into new areas, there might be competition between species that have not been in the same area before. And this is one of the things we don't know. We know we don't know. So it's a very challenging future here. Just an example, also just to mention the polar cod. The left-hand figure show kind of distribution is not right. I guess the distribution area is too wide. But we see on the right-hand figure that polar cod also lives under sea ice and is most likely one of the few fish species that do that. The question is, what will happen with the polar cod if the ice disappears? Most likely not very much, because it lives in ice-free area already in the Barents Sea and in other areas. But a lot of people have asked the question, what might happen with the polar cod? Personally, I don't believe it will change that much. Maybe the distribution area will move a bit northwards, but I think it will survive. This is much worse for this guy here, because if the sea ice disappears during summer, it will be very difficult for the polar bear to find something to eat. It's feeding on seals, and if the ice disappears early in the spring, it will be very difficult for the mothers to find food for the small ones. And I guess that's the biggest challenge for the polar bear in the future. Also, some of the seabirds might have problems. And in the Arctic Climate Impact Assessment Report, we pointed out a few species that might get difficulties in the future, while other species will benefit from increased temperature. Some conclusions. Climate variability influences marine populations directly and indirectly through the food webs, as we have seen. And the response of the marine ecosystem to climate signals varies with the periodicity of the climate signal. There are different responses to short-term changes and long-term changes. But also, there are other parameters you have to take into consideration. For example, fishing pressure may have impact on this and make it more difficult to interpret what's the impact of climate and what's the impact of fishing activities. And the major fraction of the warming in the North Atlantic and in the Arctic after 1970 is probably caused by natural multi-decadal variability. So there might be some anthropogenic contribution here, but you should not remember that the temperature we observed in beginning of this century is exactly the same as we observed in the late 1930s. So it's not changed very much since then. So it might be natural variations in the area, and not created by humans. And gap in knowledge, we need, of course, to know more about the thermal circulation. That was pointed out also earlier. Fronts in the ocean is very critical because they act as a barrier for different organisms living on the warm species on the warm side and the cold one on the cold side. And also how they are able to adapt to climate change. We know very little about that. And then we have the consequences of altered mismatch between predators and prey that might happen if the the climate is changing. And this also mentioned competition when and if new species are introduced to an ecosystem. And we need to strengthen the biophysical modeling in the Arctic, because that's, I guess, one of the key tools to get the understanding of the processes, and the only way to how to also predict what will happen in the future. And what will happen in the future is a bit uncertain. I don't know if this will be the case, but at least some people might then get a surprise. So, thank you.
I want to comment something on polar bear. I'm Tom Newberry. I work for the federal agency in Alaska that manages the offshore oil and gas industry. The effect on marine ecosystem, I think, has been relatively gradual in the Bering Sea. As you point out, the effect on the fish. The big effect really has been on the animals that depend on the ice cover, the polar bear in particular. And there it's not a linear reaction. It's not as though there's been a relatively small change in their food supply, so there's a small change in them. It's been a very disruptive change because they've lost their substrate. The substrate, the ice edge during the summer is pulling offshore. Polar bears can't catch their food when they're in the water. They can only really catch their food when they're on the ice cover. So some of them are staying on shore. They're doing what they do in the Hudson's Bay, in Churchill area. Some of them go out with the ice. The ones that are going out with the ice that have tried to swim ashore, it's been very difficult. It's not only the distance, but the polar bears aren't adjusted for the fetch, the high sea state. They're accustomed to swimming in water that's perfectly flat. Well, when they try to swim to shore and the wind comes up and there's a sea state, they drown. It's affected them in a big way. And I don't think that the effect is going to go on and on and on, because as the ice cap, the summer ice cap gets smaller and smaller, it's so far offshore that it's not going to continue to have a big effect on the polar bear population. I think they'll become, again, like the ones in Hudson's Bay, they'll become mostly, they'll stay on shore, they're fast during the summer. But that means the polar bear population is really going to be set by the number that can live through the winter on the ice. The walrus, the effect has been much more complicated. Their substrate, the ice, is moving farther north. They're feeding at the bottom. They can reach the bottom in most of the range. When that ice edge gets way off the shelf, then they too lose access to their food. A third marine mammal that depends on the ice cover, the ring seals, their dependence is primarily during the spring. And the changes during the spring haven't been anywhere near as profound as the changes during the summer. So the ring seals haven't really, the effect on the ring seal population hasn't been as dramatic as it's been for the others.
I consider this as a good comment. No, I don't think this was a good comment.
No, just I'm very curious about very interested in the lifestyle of the polar cod. And the reason is that something similar to what is happening there is happening in the Antarctic Peninsula. On one side of the Antarctic Peninsula, the ice is going away. The result is that the dominant fish species of the Antarctic fish, Ichthyophora, which is Ramon antarcticum, does need the sea ice for spawning and reproduction. And therefore they left, because they cannot reproduce anymore, and they have been substituted by mycophis, other fish species that never existed there. If the same thing happens in the, I do not know now if the polar cod also needs sea ice for reproduction, but if it does, then it has to move away too and follow the sea ice, you see. So I wonder whether you know something about this lifestyle aspect of the polar cod.
No, I don't know much about the lifestyle polar, but I know that in the Barents Sea they spawn in the northern part, but not necessarily in ice-covered areas. So in that area, I know that not depending on sea ice as far as I know. But I see that Taylor Shogol is waving his hand here. Maybe he could add something to that.
Yeah, my name is Henry Sjøldal, a colleague of Harald from the same institute. On the polar cod populations, I also wanted to make a comment that they do spawn under the ice in winter or late winter, and the eggs have a fairly long incubation period and hatches at the time when the ice starts to thaw and the spring growth resumes in the waters. The polar cod population in the Barents Sea and in the Kara Sea spawns in the Pechora Sea area, which is a very important area then for a wider part of the Arctic. For the Chukchi and Bering Sea, this is not so well known, but earlier Russian studies suggest that polar cod are migrating south and are spawning in the northern part of the Bering Sea in the winter. So this illustrates the spatial contact of these fish populations. They are migratory, they have certain habitats where they spawn, the larvae drift, and they have their migrations to feed and then back to the spawning area. So that spatial context of these small fish populations is a very important part of the Arctic ecology. And of course it can be affected. In many cases there may be positive effect because the plankton production will be larger, not only by phytoplankton, but likely also by zooplankton, which are their food. But this is also a major gap in our current understanding of Arctic ecosystems, that these small fish species, which are intermediate links between plankton and higher trophic levels, are very poorly understood. In addition to polar cod, Borealgadus saida, there is also another species, Arctic cod, Arctogadus glacialis, which there is very little information about, but it is probably a key species in the Arctic Ocean ecosystem.
Thank you for a most informative talk. That was great. That's right. Our next speaker is Ross Virginia. Ross graduated from San Diego. He got his PhD from UC Davis in 1980 on elemental cycling and nitrogen isotope abundance in natural ecosystems. And then he did a postdoc at the UC Riverside. He was a professor at San Diego State for a number of years after that, before he joined the Dartmouth faculty here. Professor Virginia's interests are ecosystem science and the impact of humans on elemental cycling in terrestrial systems. And his current focus is on both hot and cold deserts. Ross is a co-principal investigator on the McMurdo Dry Valley LTER program, but he's also done work at Toolik Lake, Alaska. Ross is, in addition to his scientific studies, he is the director of the Institute of Arctic Studies here at Dartmouth, and he teaches courses on environmental issues of polar regions, global environmental science, and ecological agriculture. So I welcome Ross.
Thank you, Mary. This is my opportunity on behalf of the Institute of Arctic Studies to welcome everyone here. And what I want to do this afternoon is talk a little bit about climate change and its impact on terrestrial ecosystems. And I want to pick up on this comparative polar model. I've been very pleased with the amount of Antarctic content at Arctic Science Summit Week. And I think it's very important for us to think about in IPY the role of these comparative studies and teasing apart the important interactions that control both the Arctic and the Antarctic ecosystem. So this talk is really about how climate affects species abundance and biodiversity, and the impacts of that on nutrient cycling, and particularly the carbon cycle. And I also, again, want to stress the importance of the comparative studies that are emerging within IPY. And sort of an overview of that, we're finding more and more that both the Arctic and the Antarctic systems are sort of exquisitely sensitive to very small variations in temperature. And we're trying to understand the mechanisms that control these responses, the feedbacks, and the cascading effects that contribute to terrestrial ecosystem response to climate. I'm going to talk about two different approaches that we're using in these comparative studies. One is to take advantage of large, well-funded multidisciplinary sites and teams that are working in various ecosystems. And this is the NSF-funded LTER, Long-Term Ecological Research Network. And you can see there are a lot of sites. I think there's 26 sites distributed throughout North America, spanning the tropics to polar regions. There are two sites in Antarctica, the McMurdo Dry Valleys, where most of my research is done, a polar desert. The other site is the Palmer Peninsula up here, which is a site dedicated to understanding the marine ecosystem, but also the interface between the terrestrial and the marine. We're fortunate to have a balance. We have two sites, LTR sites in the Arctic. We have the Arctic Tundra site near Toolik, and then we have a boreal forest site at Bonanza Creek. So we have an opportunity then to take advantage of these large, well-funded teams working in these sites for long durations to develop a synthesis about terrestrial systems and how they are responding to climate. So this is one of the opportunities that we have, is to take advantage of these existing networks. The other approach is to design smaller, more specific and less expensive experiments that can be moved around from place to place and ask a more specific focused set of questions, a set of hypotheses, and then observations that can be brought together by groups to develop a synthesis of how terrestrial systems respond to change. And I think one of the best examples of this is the ITEX program, the International Tundra Experiment. And there have been a number of recent synthetic volumes coming out about ITEX. ITEX works on this very simple principle. One can take and place an open-top chamber on the ground. It acts like a mini greenhouse, and you can warm a piece of Antarctica or a piece of the tundra, and then look at the response to this simulated climate change. And you can see in this that the degree of the change in most of these experiments is 1 to 3 degrees. That's roughly the lower to mid-range climate change that we're going to be experiencing in many of these locations. So it's a reasonably realistic simulation, and it provides a simple treatment, but a lot of power in teasing apart how plants, soils, soil biota, and exchanges with the atmosphere respond to the presence of these open-top chambers. Okay, well, I'm going to jump back now and start with the LTR network. This is a simple plot just showing the range of average annual temperatures and precipitation for all the different LTR sites. And you can see where the Antarctic and the Arctic sites fall. You can see, oops, sorry about that. Let's go back. There we go. The McMurdo is the end member. It's a polar desert site. But I put this up in part to show that, yes, the polar sites are cold, but they are part of a network of sites. And I think one of the important things about IPY is that our study should contribute to the understanding of all terrestrial ecosystems, and that we are part of this larger network. Okay, so let's go to McMurdo, the McMurdo Dry Valleys. And you can see where we're located in Antarctica. We're supported by McMurdo Station. And we've been trying to understand how climate has been changing in Antarctica and how the terrestrial systems and linked aquatic systems and the ice systems too are responding to climate variation. This is a synthesis of climate change on the Antarctic continent. It was published in an article by Peter Dorn in 2002, and this climate work was done by John Walsh, who spoke earlier today. And if you look at the change in temperature in the Antarctic continent, you can see a couple of patterns here. One is that over the continental area, you see a slight cooling or a relatively modest change in temperature, and McMurdo's sort of over in here. But compare that to the Antarctic Peninsula, you can see a very rapid and large change in temperature in these two places. So we also have these contrasts. Some parts of Antarctica that are changing, either warming or slightly cooling. Other places are strongly warming. So again, that gives us an opportunity to understand the range of terrestrial response to climate change. So here we are. Here are the dry valleys. This is Taylor Valley. And we've seen, I'm going to document that we've seen both warming and cooling in this system over the last couple of decades. But the models predict a much warmer future. And so we need to begin to think about what is the future of the Taylor Valley and the dry valley ecosystems. You can see that we have large ice-free areas, hence dry valleys. We have glaciers coming down, into alpine glaciers feeding into these valleys. These are ice-covered lakes. This is the McMurdo Sound, the Ross Sea, and way over here is Mount Erebus and the site of McMurdo Station. So one of the major objectives of the Dry Valley LTR system is to understand the dry valleys as a polar desert and how each of the components that make up the dry valleys are connected, the transfers between them, and in particular how biodiversity and life alters the functioning of the system and how species change might affect the future of the dry valleys and their functioning. You can see a very large amount of dry soil, and that's the system that I'm concerned mainly with. But this soil is linked very closely to streams, and streams deliver nutrients to the lakes. And then the water that's draining into those streams is driven by changes in glaciers. So we're very interested in the linkage of these systems, how small changes in climate affect these linkages and in response to the entire ecosystem. So what do we know about the history of climate in the dry valleys? Well, the first people into Taylor Valley, Antarctica were part of Robert Falcon Scott Discovery Expedition. And here they are shown very comfortably leaning against a hot rock on the top of Taylor Valley on Christmas Day. And so we have their journals, we have some photographs. And no one was to return to the dry valleys until Robert Falcon Scott's second expedition and the Terra Nova expedition. And fortunately, they did leave behind some photographs, which gives a snapshot of how the system looked nearly 100 years ago. And we have a comparison here of some photographs that Andrew Fountain put together. On the left is 1911. This is the face of the Taylor Glacier, and this is the edge of Lake Bonny. Okay, Andrew Fountain was able to go back and match the photograph up. You can see the appropriate rocks here. And now look at the margin of Lake Bonny. The lake has risen, all right? A very strong indication that something about climate or precipitation or some interaction has occurred since 1911 when Robert Falcon Scott's crew came into there. So it suggests over the last 100 years or so there's been some sort of net change, net warming in the dry valleys. Well, fortunately, we've had a long-term ecological research program there to actually take measurements and to look at trends. And rather than a warming, what we've observed over the last 2 decades has actually been a decline in temperature in this part of Antarctica, certainly in the dry valley regions. And that this decline in temperature is significant. We can measure it, and it's particularly important in the summer. We've about a 1.2 degrees centigrade per decade change, which is a large temperature change. So what does that mean to the ecosystem? Is it important? Is it significant? Is it real? And we went over our climate data over and over to begin to convince ourselves that it really was getting cooler. But when you started looking at the lakes, you could see how these changes in temperature were manifest in changes in the physical system and the linked biology. The panel below shows the change in ice thickness on the lakes in the dry valleys. And you can see that as the valleys were getting colder, the ice on the lakes is getting thicker and thicker. Okay, very consistent with that climate cooling of the dry valleys. What's important about this is that this cooling and this change in the physical system, this change in state of water and accumulation of ice, ripples through and has very strong effects on the biology of the dry valleys. And we've already seen examples of that in the marine system, and we've been throughout the day, and we'll hear more, I'm sure. But one of the major consequences of more ice is less light penetrating that ice into the water column, less energy for photosynthesis, for production in the lakes, and all that ripples through the aquatic food web in these lakes. So a change in climate, change in physical conditions, a change in biodiversity, and a change in ecosystem function within the lakes. So what about the soils? This is the system that Diana Wall and I and our colleagues have been working on since 1989. And when Robert Scott's men went into the dry valleys, they talked about the valleys of the dead, that there was no visible life there. This is a sterile, barren environment. And to many people, it still looks that way. But if you take out a handful of soil and you have a good microscope and some curiosity, you'll find out that the soils, in fact, are teeming with life. Very low diversity life, but life is there. And that as Edward E.O. Wilson puts it, the big critters, the dominant animals there aren't the lions and tigers, but they're actually these microscopic invertebrates. And the most important of them in the soils of Antarctica are microscopic roundworms or nematodes. They're the top of the food web. They graze on bacteria. They control the rates of carbon cycling and nutrient cycling in these soils. So we've been very interested in how this animal might be an indicator of climate and climate variation in Antarctica, and whether or not soil life will respond to climate variation. We've seen a lot of downward trending graphs and presentations here, other than maybe CO2. But here's a response plotting nematode abundance in soils during that period of cooling in the dry valleys. And you can see a remarkable decline in what is the dominant animal in this soil system. It's very striking, and we've spent a lot of time thinking about this and doing work to follow up on it. First off, you might ask the question, does it really matter? You know, these nematodes are declining, well, so what? What can we link that with? What are the important, what's the function of this animal, and what does it tell us about links between biodiversity and ecosystem functioning? We've done a number of experiments in the field where we've added stable isotope tracers to look at the relative importance of nematodes in the carbon cycle there. And then we've used those results and extrapolated that back to what's happened to these populations. We've seen a 2/3 decline in the number of nematodes during this cooling cycle in the dry valleys. And based on that percent decline in the role of these nematodes in the carbon cycle, we think we've seen about a 1/3 loss in the carbon cycling potential of this ecosystem from this decline in this one sort of key species. So one of the values of these polar systems is their low diversity and the ability to tease apart these relationships between species abundance and what they're really doing in the ecosystem. And that's one of the hallmarks of the McMurdo Dry Valley system. Well, what about not just this nematode, but we actually have communities of life in these soils? And how do more complicated assemblages of organisms respond to climate variation? And one of the approaches that we're taking here is to go out and very carefully document what soil conditions are associated with the distribution and abundance of different critters in the soil. And we can use a variety of statistical approaches to try to figure out where in this multivariate soil chemistry, soil climate space, different organisms prefer to live. And so we can divide the environment up into sort of what would be our cold ecosystems, which tend to be dry and alkaline, and what would happen if we had a warmer, wetter world in Antarctica. We have organisms that prefer this type of habitat. And so if we predict a cooling future for the dry valleys, it will tend to favor this organism, Scottnemma, which happens to be the dominant one in the ecosystem. If we begin to see a warming and wetter Antarctica, we think that the communities dominated by these organisms will probably be favored by this climate change. So we begin to get some insights on how communities of organisms may respond by very carefully documenting and understanding their specific niche or life requirements. I've already shown, I introduced the ITEX experiment with open-top chambers as a way of modifying or manipulating climate. And we're doing some of this work in Antarctica as well. And here's an experiment where we have out a grid or a network of these open-top chambers to warm soil. And then, in addition, we're crossing this experiment with adding water. So we're warmer, or we're warmer with water, or we have sort of a control experiment, control treatment. And what do we find? After a number of years, we see in this experiment this particular response. The first graph is the control, the untreated experiment. When we put a chamber over there and make it warmer, which you might think would make it a more favorable environment for life there, we get a decline in nematode abundance. If we had water there to sort of, with the warm plot, maybe there's a little increase, but still that number's lower than a control plots. And it's only in the treatment where we haven't manipulated temperature, but we've added water, that we get some kind of response here. So it suggests that the response is complicated, that there's probably a temperature and water interaction, but the warming, at least for this organism in these soils, is probably going to have a detrimental effect on the population of Scott nema, the dominant nematode in the ecosystem. Okay, well, let's move over to the other side of the continent and look a little bit at the peninsula. Peninsula is well known for the very rapid rate of warming that's occurring there. Plus 2 degrees since 1950, 4 degrees centigrade per decade, and in all the climate projections, that's like the most darkly colored segment of Antarctica. So this is where climate is changing rapidly. And that's the location of the Palmer Peninsula LTR, which is part of this experimental network. There's a very wide network of open-top chamber experiments that are being placed along the Antarctic Peninsula, right on up into sub-Antarctic islands, Falkland Islands. And this is an international network involving the British Antarctic Survey, collaborators from a number of European countries, and we hope increased participation from US scientists. There's quite a bit of this type of work going on at Palmer as well. And so here's a picture of these chambers put out in the field, and you can actually see some vegetation, all right? This part of Antarctica, we have 2 vascular plant species, 2 grasses, we have mosses and lichens, so we have something that looks alive in vegetation. That's a forest on the Antarctic Peninsula. And what do we see there? Well, again, these are new results coming out from this study. In this one particular experiment, in as little as 3 years, they see a very dramatic decline in lichen species in these open-top chambers. It's a little difficult to see with the lights on up here, but there is a dramatic decline in this very slow-growing lichen species. Should have significant effects on the cycling of nutrients and the soil biota in the system through time. Okay? So we know these systems are sensitive to change. Other locations on the peninsula see where the grasses occur, see very marked changes in when the grasses flower, when they set seeds. So the whole life cycle of the biology, particularly of the plants, is responding to climate warming in these systems. Okay, so far we've seen that in Antarctica, the systems are sensitive to temperature change. That change can either come from cooling or warming, but nonetheless, these systems are very sensitive to variations in temperature, and we need to tease those interactions apart. Very similar sets of experiments are going on in the Arctic, and many more sites, in fact, are being investigated. This is the Arctic LTER site at Toolik Lake. A lot of work there being done on tussock tundra ecosystems and their response to climate variation. There's a very large and extensive network of these ITEX chambers being distributed throughout the north, not just Toolik Lake, and all of them with a common vision of trying to understand how the coupling between plants and changes in soil respond to temperature, and then the feedback interactions that occur from there that further change plant communities and their function. There's the very important and interesting meta-analysis of the ITEX chambers and the work that's come out of this is recently published by Skip Walker and colleagues in 2006. And this shows some of the important changes that we can see across these ITEX experiments from different locations. And if you focus sort of on, whoops, I'm sorry, keep doing that. This end over here, one of the most important and significant changes we're seeing is an increase in woodiness, and the increase in the abundance and the stature of shrubs. So we're moving from systems dominated by grasses lichens and forbs to woody-dominated systems. And this is a huge effect in terms of the animals that live on these ecosystems and their response to changing vegetation. So the Arctic is becoming more woody in part in response to this climate variation. So we've looked at just quickly sort of 3 different types of systems and how they're responding to climate manipulations or warming. If you look at the polar desert of McMurdo Valley, warming seems to reduce soil moisture, at least that's what we're seeing. It results in the decline of the big animals, the soil invertebrates, and we're able to link that with a change in the carbon cycle. So all the pieces of the story sort of come together there. The Antarctic Peninsula, what do we see there? We know it's warming rapidly. We can see that naturally. We can also see the response of that system to warming by these ITEX experiments and putting out these networks of research plots. There, one of the strong responses we see is a decline in the non-vascular plants. We see a decline in lichens and mosses. We don't see the same response at every site, and that's one of the most important take-home messages, particularly from the work in the peninsula. It's very important to understand the idiosyncratic nature of many sites, the pre-existing soils, any history of disturbance, the legacies of past vegetation that carry over to the current vegetation. So that variation, in fact, is actually richness of information about how these systems may respond to warming in the future. When we look at the Arctic tundra ecosystems, we see that warming, one of the clear responses there is an increase in woodiness, an increase in the abundance of shrubs. And there's a lot of work now going on trying to understand what that really means and what the linkages are in response to that woodiness. So we can see this change. We can see that the terrestrial systems respond to warming, and they also respond to small amounts of cooling. But what are the drivers of this change? And where should our research be focused in terms of understanding the mechanisms behind this? Well, one revolves around soil moisture. All of these experiments show a strong interaction between soil moisture and warming. And we have a relatively poor understanding of that linkage and being able to make predictions about how warming in various ecosystems contributes to changes in soil moisture. And I think in the next talk on permafrost, we'll see better how that might come together. We can see that warming changes the vegetation. Shrub increase in the Arctic have many effects. One is that they capture more snow. The snow insulates the soil. That allows warmer soils, prolonged microbial activity. It changes the nutrient cycle in ways that favor more shrubs. So shrubs begat more shrubs. So we end up with a positive feedback cycle triggered by the initial warming. And finally, in this comparison, we're beginning to see very clearly that changes in species diversity and abundance have clear effects on nutrient cycling in the carbon cycle. And we can see that simple example from the dry valleys. Okay. So what can we take home from this? Well, one is that both polar regions are responding to small changes in temperature. And that the effects of these small changes in temperature are amplified by the feedback mechanisms and the linkages between plants, soils, life in soils, and the atmosphere. So what are the opportunities, perhaps, and some of the challenges for this comparative work and IPY? Well, one is already happening. That is that the existing networks like ITEX are being connected together more fully through a large number of related IPY projects. Just go on IPY and Google Polar Comparison and you'll see the long list of projects that are coming out and doing this. We have sort of young networks that are growing and expanding and bringing new techniques to these polar comparisons, and Tarantella is an example of that. And finally, I'm hopeful that one of the things that comes out of Arctic Science Summit Week and some of the discussions here are what are the next new experiments? What are the next ITEX type approaches to understanding the response of terrestrial systems to climate change in both the Arctic and the Antarctic? So I'd like to thank a number of people from the McMurdo LTER and some colleagues to try to get me back up to speed on Arctic terrestrial vegetation and climate change. And I'd be happy to take some questions. Thank you.